Okay, so we're now on to chapter 6, which is part of the AS stuff, which is for linear programming. And actually, chapter 7 links to this, but is only in A2. So, really, the best way to explain to you about what linear programming is to kind of show you an example about an actual linear program, which is down here. But the gist of linear programming is trying to maximize or minimize something with lots of constraints that might be happening. And here is the example that I'm going to go for. So, first of all, I've said that Mr. Bison is making two types of cake, lemon drizzle and carrot cake. Alongside other ingredients, each lemon drizzle cake needs 1 egg, 250 grams of flour, and 200 grams of sugar. The carrot cake requires 2 eggs, 300 grams of flour, and 300 grams of sugar. He has 24 eggs, 4 kilograms of flour, and 5 kilograms of sugar. He will sell the lemon drizzle cakes for £4.50 and the carrot cakes for £5. And he wants to maximise the money that he can make, assuming all the cakes will sell. Now, obviously, this is not particularly real life in this setup because I could just go out and buy more eggs or more flour or more sugar, and I could change the price of the things that I'm going to sell at. But you can see how this could begin to apply to lots of real life situations where you couldn't go out and buy more things, or it might be talking about a factory with the resources that are available to it. So this problem that we've got here, that we're going to try and maximize the money that can be made, what we do is we change it into a linear program. That's the name of kind of what this thing is that we've got down here. Whenever you're going to write one of these linear programs, which you'll be doing throughout this topic really, you should always just declare what the variables are going to be that you're going to use. And these variables are called the decision variables. X and Y here are the decision variables because those are the things that we can make the decision about. How many lemon drizzle cakes and carrot cakes am I going to make? So you should declare that X is going to be the number of drizzle and Y the number of carrot cakes that we've got here. So X and Y are our decision variables. And then what we're going to try and do here is we're going to try and maximize something which is called our objective function. And the function that we're trying to maximize here is p equals 4.5x plus 5y. Now I'm hoping you're thinking, oh, I can see where this has come from. P here is going to be referring to the profit. I want to maximize my profit. And the number of lemon drizzle cakes would get multiplied by 4.5 because that's the cost of the lemon drizzle. And the number of carrot cakes would get multiplied by the 5 because that's the cost for a carrot cake that the price has been set. But I can't just maximize this because I can't just make as many of the carrot cakes as I can, assuming that they're all going to sell, because I have a restriction. I have some constraints on the ingredients that are available to me. And so this is the constraint section that we've got down here. I've got 1, 2, 3 constraints and this non-negativity constraint as my fourth one here. So the things that it is going to be subject to is that x plus 2y must be less than or equal to 24. And I'm wondering if you can think where this has come from. This is to do with the number of eggs. I've got 24 eggs, and the number of lemon drizzle cakes plus 2 times the number of carrot cakes will give me the number of eggs that I would be using. So x plus 2y will tell me how many eggs I'm going to use, and it's essential that the eggs I'm going to use for the cakes will be less than or equal to 24 because I only have 24 eggs available to me. And you can similarly see that this constraint that we've got here is referring to the flour. I have the 250 that goes with X and the 300 that goes with Y and the 4 kilograms. So I've got 0.25 putting it into kilograms with X, 0.3 with Y, and the 4 kilograms here. And similarly, I won't go through this one in as much detail. You can see how the last one is referring to the amount of sugar that I have, which is the 5 kilograms, the 200 grams for the lemon drizzle, and the 300 grams for the carrot cake that we've got there. And I've written something like, how could we rewrite these two constraints here? Because you might see these constraints written in alternative ways after this particular part is set up. And I guess the way we would probably do this is we don't usually like having decimal kinds of coefficients. So what I could do is think about multiplying this and simplifying this equation. So if I say multiplied everything by 100, I would end up with 25x plus 30y is less than or equal to 400. And then I could divide everything by 5, so I get 5x plus 6y is less than or equal to 80. So these three constraints that I've got here are all the same. And you can see what would happen with this one that I've got down here. If I was going to rewrite this constraint, I could times it all by 10, or I could times them all by 5. Not 5, actually, I'll times them all by 10. So I could get 2x plus 3y is less than or equal to 50. So just be warned, you may need to rewrite them to have them with integer coefficients. And then the last one that we have down here are the non-negativity constraints, because I also need to say my x and y values have got to be greater than 0, because I can't make a negative cake here. Now, I guess there are some other constraints that we might have that we don't list here. One of the constraints might be that X and Y have to be integers. I'm not going to really make half a cake and then sell it for half the price. That doesn't really make sense in the context of this problem. So there might be a constraint when we come across these problems about things having to be integer values as well. So this is what a linear program might look like. Hopefully you can see how all of these things here are connected to the text that we've got. And then my last thing is to kind of describe to you about some of the language that we'll be using in this topic. And I've put them all in green because they're all to do with different solutions that we've got. So the feasible solution, or a feasible solution, are values for X and Y that satisfy the constraints. So for example, I could just make one carrot cake and one lemon drizzle cake. So X and Y could both be 1, and I would definitely have enough eggs, flour, and sugar to do that. But I wouldn't be maximizing the profit that I could make. But it's still feasible that it satisfies the constraints. The feasible region is the range of values for X and Y that satisfy the constraints. So there's going to be some ranges of X and Y that will satisfy all of this, but they're linked to each other because you might be able to make lots and lots of lemon drizzle cakes, but that restricts the number of carrot cakes that you could make. So it's a feasible region because when you see this later on graphs, you'll see that it's like an area on the graph that is linking together X and Y. And then last of all, the thing that we're really looking for here is the optimal solution, the values for X and Y that fulfill the objective. And in this case, the objective is to maximize my profit. So what we're really trying to do is think, what values of X and Y am I going to pick that will make me the most money in trying to sell these cakes that we've got here? And that's kind of the essence of what linear programming is going to be. It's always going to be about trying to solve a problem where there are lots of constraints that make the decision making quite challenging. So just to talk through what we'll be doing in this chapter, we'll be beginning about formulating linear programs. We'll then be thinking about how we take these things here and we represent them on a graph. We'll then actually be finding the optimal point, which is the same thing as the optimal solution. And then we have this restriction on the fourth exercise, which is where we need to make sure that some of our questions need to have integer solutions because it may not be possible to kind of split up the number of cakes into sort of decimal values of cakes. And that will always be kind of indicated either by the question explicitly or by the context of the question that there might be. So what we're going to do is we're going to have a look at one of these examples here that we're going to do formulating our own program, our linear program. And then in a separate video, I'm going to go through some things that are maybe a bit more challenging about some of the language that they use here. So this one says that a company buys 2 types of diary to send to its customers, a desktop diary, which I'm guessing there just is a bigger diary, and a pocket diary. And it's a very old-fashioned example because I don't really know who uses diaries. I imagine most people are using stuff on their phones or computers. But anyway, it says they will need to place a minimum order of 200 desktop and 80 pocket diaries. They will need at least twice as many pocket diaries as desktop diaries, and they will need a total of at least 400 diaries. Each desktop diary costs £6 and each pocket diary costs £3, and the company wishes to minimize the cost of buying the diaries. And we're going to formulate this as a linear programming problem. So one of the first things we always need to do is to assign the decision variables. So what I'm going to say here is I'm going to say, let the number of desktop diaries bought be X, and I'm going to let the number of pocket diaries bought be Y. It's always important you have those kind of first bits to tell them exactly what it is that's going on here. So when I go through each section, we need to place a minimum order of 200 desktop and 80 pocket diaries. So one of the things we're going to say here is that the desktop diaries have got to be, in fact, in a second, I might leave a little space because we're going to decide what we're going to be minimizing or maximizing. So the desktop diaries have to be at least greater than or equal to 200. And there needs to be a minimum order of 80 of the pocket diaries. So the pocket diaries have got to be greater than or equal to 80 that we've got there. Now, the next thing says they will need at least twice as many pocket diaries as desktop diaries. Now, people usually, when they read this and they see twice as many pocket diaries, which is Y, as desktop diaries, which is X, they usually say, oh, 2Y is equal to X, or 2Y is sort of as greater than X, like this. Now, this is actually the wrong way around for this, because if you think about this as though it were an equality that we have here, that 2Y is equal to X, this is saying that the number of the desktop diaries is the number of the pocket diaries multiplied by 2. So the number of desktop diaries, let's say that y was equal to, say, I don't know, 10, then x would be equal to 20. And it's the other way round how people usually think this, because this is actually saying that we would have 20 desktop and only 10 pocket, but actually we're saying we need twice as many pocket as diaries, as desktop. We need more of the y than we do of the x. So it's actually the other way round from this. It would actually be something like 2x and y, because if you think about it, the number of pocket diaries needs to be twice the number of desktop diaries, and actually the number of pocket diaries needs to be at least twice, which means that it has got to be greater than or equal to 2x, at least twice. So it could be twice, but it could also be more than that. So I'm going to put that extra constraint that we've got here as 2x is less than or equal to y, and just be on the lookout that it's often the other way around to how your brain initially thinks that it should be. We've then got this statement that says we need a total of at least 400 diaries. Well, the total would be the number of the X diaries and the Y diaries, and it needs to be at least 400, which means it could be greater than or equal to 400. It says that the company wishes to minimize the cost. So what we're going to try and do is we are going to try and minimize our cost function. You can either use C or P. I'm going to use capital C here. We're going to try and use the minimizing of the cost. Now, a desktop diary is £6, so the total cost would be 6 times the desktop diaries plus the £3 multiplied by the pocket diaries that we got there. And then the language that we use is we say we minimize that objective function subject to these constraints that we've got here. Now we should always say the final constraints, which are the non-negativity ones. So we also need to say that x and y have both got to be greater than or equal to 0, because you obviously couldn't buy a negative diary that we've got there. So I'd say the only difficult one is this one, but we're going to delve into that language a little bit more in the next video, where we try and formulate some linear programs that have much more challenging and complex language that go with them. Me again, just realised this isn't actually necessary in this one, because we've already said that x and y are greater than 280, so we don't need that non-negativity one because it's already covered with those two inequalities.